Hey guys, welcome back. And hopefully you did okay with the dimensional analysis. We're back to the math part of chemistry, but this time we're going to take our balanced chemical equations and put mathematical quantities to them. Fun, fun, fun. So you're going to need eventually your periodic table out, and you will also need your calculator. So please make sure you have both those with you as we go through this PowerPoint. Now, let me share my screen with you here. And I'm going to put me way down here at the bottom. And let's view this. Now, so we're going to do chemical quantities, and this is chapter 10. So we kind of went backwards. And you can see this is a thing called a mole map that we're looking at right now. You'll use it in a little bit. Quantities refer to how much of something you have. Sometimes we use words to indicate a certain quantity. For example, when I buy pencils for the school year, I order them by the gross because I use a lot of pencils. A gross of pencils is 144 pencils. I don't call Office Depot and say, hey, I want 144 pencils or I want 288 pencils. I buy them by the gross. I scroll down. A gross, as you can see, it's kind of two different quantities here. There's 12 pencils, so 12, there's 12 in this box. 12 times 12 is 144. So they actually come in dozen packs, but you get 12 1 dozen packs. That leads us to the next one, a dozen. A dozen is the same as the quantity 12. Okay, so if you get a dozen eggs or a dozen donuts or a dozen whatever, it equals 12. I would know what you're saying if you said, I need a dozen of these. You don't have to say the word 12. I know what a dozen means. When we buy paper for school, we buy it by the ream. One ream of paper is 500 sheets of paper. So we call up Staples and say, we need so many packets, so many reams of paper. And each ream is a packet of 500 sheets of paper. So it doesn't matter if I say ream or 500. It's the same thing. And then, of course, a couple. We know a couple means two. It could also be a pair. We've got a couple words now, a couple words for the number two. Pair, couple. So I say, hey, go get me a couple of chairs. You'd bring back two chairs. If I said, go back, bring me a pair of earrings, you bring two earrings. Okay, so there are words that we use for numbers, and we know that these two are the exact same thing. Now, in chemistry, we use a term called a mole. A mole is a number. A mole is a unit that's associated with a certain number. So mole is a unit of measurement in chemistry. It's a certain number of particles. Now, that number, oh, the mole. Yeah, we always put the mole up here because it's a mole, but it's not that kind of mole. That's a mole that digs in the ground and stuff. That's not the kind of mole we're talking about. A mole is an abbreviation, I'm assuming, for some form of molecule, but I really don't know where the mole came from. I guess I could look it up one day. Anyway, so, but a mole is a count. It is a count. It is a certain quantity. Just like a dozen is 12, just like a few is 3. A mole is a really big number. Let me show you. Enjoy.
Mole is an animal that burrows in the ground, or a spot on your chin that you gotta shave around. But there's another kind of mole of interest to me. That's the kind of mole they use in chemistry. A mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. much too big a number to comprehend. Now say you had a mole of pennies to distribute round the world. Give to each of the 5 billion grown-ups, boys and girls. There wouldn't be a single soul down and out of luck, because everybody in the world would get $1 trillion. Or say you had a mole of paper and stacked it toward the sky. Paper's awful thin, but that pile would get so high, you'd reach up into outer space. In fact, I think you'd find it'd go up to the moon and back 80 billion times.
Holy cow.
And a mole is a unit, well, have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. Now suppose a mole of marshmallows fell upon the planet. Over each square inch of land and sea, you think that you could stand it? That layer would be 12 miles high and, of course, block out the sun. We're talking close to 5 million trillion tons. Well, maybe we could save ourselves if we all started eating 1 marshmallow each second. Not 2, because that'd be cheating. With 5 billion people munching, how long you think it'd take? 40 million years, and that's without a bathroom break. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend. But say you had a mole of atoms, would the pile be immense? Should I say the answer now or leave you in suspense? Well, atoms are so very, very small, you understand. You can hold a mole of atoms in the palm of your hand. So shake a little sugar in the middle of your palm. Now you don't want to spill it, so try and stay calm. You hardly can imagine and barely realize there are more atoms in that sugar than stars up in the sky. And the mole is a unit, or have you heard, containing 6 times 10 to the 23rd. That's a 6 with 23 zeros at the end. Much too big a number to comprehend.
Isn't that fun? A mole is such a big number. I mean, the fact that if you had a mole of, paper stacked, it go, up to the moon and back 80, I think it said billion times. I mean, that's crazy how big this number is. Yet that number is so big, you can hold a mole of sugar in the palm of your hands. In fact, a mole of water is about 4 tablespoons. That those atoms are so small that you could hold a mole of them in your hands. It just gives me goose pimples. Okay, so a mole is equal to 6.02 times 10 to the 23rd. And we say it is of representative particles. A representative particle is just anything you're talking about. For example, if I say, go get me a dozen eggs, you'd bring back 12 eggs. Eggs is a representative particle. It doesn't matter what you're talking about. That's what we're counting. If I say, go get me a dozen pencils, a dozen is 12, no matter what. So a mole is 6.02 times 10 to the 23rd, no matter what. Look how big this number is. Look how big that number is. It's crazy. It's huge. It's just unfathomable. Now, this is the guy who came up with it. Oh, and by the way, I looked it up during the video. Mole does come from molecule. I thought it did, but I wasn't quite sure. So this is the guy who came up with this number. It's called Avogadro's number. So it's a mole. He gave the term mole to 6.02 times 10 to the 23rd. That's what he did, okay? This is Amedeo Avogadro. Now, here's a little video about Mr. Avogadro.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Fortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers,
Yummy.
which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth.
Wow.
If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is,
You should know this.
anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, so basically, that's a mole is just a number, okay? And like you said, we're just not familiar with it. We understand what a pound is. We understand what a dozen is. We understand what a few is. But a mole, we're like, a mole? There's just so many other words we associate with the word mole. It doesn't seem to like it should be a number for us, but it is. It's 6.02 times 10 to the 23rd of whatever we're counting. So what do we typically count in chemistry? Well, we count atoms. So if we're looking at elements right here, like the element copper, we're going to count by atoms. So we'll say, so many atoms can equal so many moles. If we're talking about a covalent compound, we're going to look at molecules. Water is a covalent compound. And by the way, I said tablespoons earlier. I meant teaspoons. So 1 mole of water is about 3.6 teaspoons of water. But molecules are associated with covalent compounds. So when we talk about covalent compounds, we use the unit of molecules. And of course, then sodium chloride is an ionic compound, and its little packets are called formula units. Okay, so elements, atoms, covalent compounds, molecules, ionic compounds, formula units. That's the type of unit we use with them. Okay, so a representative particle refers to any of the following. An atom is a single element. So if I say I have a mole of atoms, 1 mole of atoms is going to equal 6.02 times 10 to the 23rd atoms. That's it. 1 mole of anything equals 6.02 times 10 to the 23rd. So single elements, we talk about atoms. If we're talking about molecules, which is a covalent compound, they make up the covalent compounds. 1 mole of CO2 is really 6.02 times 10 to the 23rd molecules of CO2. Why are we using the term molecule? Because carbon dioxide is a covalent compound. Now, what if I took an ionic compound and I dissolved it in water? Well, it comes apart into its different ions. So 1 mole of sodium ions is going to be equivalent to 6.02 times 10 to the 23rd ions of sodium. It's a representative particle. What about ionic compounds? It's a formula unit. So 1 mole of sodium chloride is 6.02 times 10 to the 23rd formula units. And I know it's a formula unit because sodium chloride is an ionic compound. So you have got to recognize, is it a covalent compound? Is it an ionic compound? Or is it just an atom or element? So you go way back to chapters, was it 7, 8, and 9, and remember this, okay? So you've got to remember, 1 mole of anything equals 6.02 times 10 to the 23rd. That's it. 1 mole of anything is that number, just like a dozen of anything is 12. It's just a number associated with a word, okay? Whoop, a little spinning motion there. Now, here's the fun part. We're going to convert between moles and particles. You're like, particles? Well, remember, particles are your atoms. Particles are your formula units. Particles are your molecules, and particles are also going to be your ions. So we're going to go between a mole and a particle. It would be kind of like saying, going between a dozen and the individual eggs. If I buy 4 dozen eggs, how many eggs do I have? 48. If I buy 3 reams of paper, and each ream is 500 sheets, I've got 1,500 sheets of paper, right? If I buy 2 gross of pencil, I've got 288 pencils. So the particles are what we're counting. And the mole is obviously our chemical quantity. So let's look at this. So we have a mole, and we have to get the particles. Okay, and I'm going to move this up here. So we're going to go between moles and particles. Now I'm going to have to get a way to draw this here. So we've got to go between moles. Oh, I was going to go moles and particles. We'll go this way first. So we're going to go, let's see, let me erase that. I don't like this. I'll do more of these online here, or actually drawing here in a second. So we're going to go from moles down to particles. Excellent. Okay. So when you go from a mole to a particle, remember dimensional analysis, whatever you're looking for typically goes on top. So I start with mole. Okay. So when I go from a mole to a particle, I'm going to multiply it, okay, by 6.02. See if I can do this. Times 10 to the 23rd. Over 1 mole. Now look at this. You're like, whoa, that's kind of silly. 1 mole equals 6.02 times 10 to the 23rd. These two are the same thing. So basically it's like multiplied by 1. But you're converting from a certain particle, from a mole to a certain particle. It all depends what that particle is going to be. I wish I had a pen that would do this. Okay? So if I'm going from mole down to particles, I'm going to multiply by this. If I'm going to go from particles up to mole, what I want to do is this then. I will say, okay, 1 mole goes on top. And on the bottom is 6.02 times 10 to the 23rd particles. I'm just going to write a P here if you don't mind for particles. So depending on what I'm going, if I'm starting with moles and I'm heading to particles, I use the red conversion factor. These are called conversion factors or equivalent statements. They mean they equal the same thing, an equivalent statement. 1 mole is the same thing as 6.02 times 10 to the 23rd. They're equal. So if I'm going from a mole to particles, I use this. If I'm going from particles to moles, I would use this conversion. And I multiply by it. Okay? So let's go a little farther into this. Let me see if I can erase all these things real quick. I should have used the original one to hit it on it. Okay, so mouse. So what we're looking at is this. 1 mole of anything equals 6.02 times 10 to the 23rd particles. That's it. So we're going to practice some of these. Now, it says moles to particles. I'm going to do this on the, using the hover cam. I think it'll be a little bit easier for you to see. But it says, given moles, so if I have particles, or I'm looking for particles, I'm sorry, if I'm looking for particles here, and they gave me how many moles, I'm going to multiply this because moles on top and moles on bottom will cancel each other out, and particles will be left behind. So now it says, propane is a gas used for cooking and heating. My question is, how many molecules of propane are in 2.12 moles of propane? Okay, so now we're going to switch over here. I'm going to stop this share. I'm going to share over here. Advanced. Let's see if this happens. There we go. Okay, let me get rid of this. Okay, so, oh goodness. There we go. Let's lock it in. So, here's how you do it. So it says, how many molecules will equal 2.12 moles of propane? That's what it wants to know. So the first thing you do is write down your given. This is my given. My given is the number that's given to me. So I'm going to write down 2.12 moles of propane. Doesn't matter if you know what propane is or not. It's just what it is. Just write it down. Okay? So then I'm going to multiply by something. So to try to go from moles to molecules. That's what I want. I want to convert my units from moles to molecules. So if moles is on top, in order to convert it, moles has to go on the bottom. Okay? Moles on top, moles have to go on the bottom. Now you got to remember, what's our conversion factor here? Our conversion factor is this. 1 mole of anything equals 6.02 times 10 to the 23rd particles. Now remember, that particle could be molecules, it could be ions, it could be formula units. In this case, it's molecules. So we're going to write down 6.02 times 10 to the 23rd molecules equals 1 mole. This is an equivalent statement, guys. It doesn't matter. These are exact the same. I could have 1 mole over 6.02 times 10 to the 23rd, or 6.02 times 10 to the 23rd over 1 mole. But the thing is, it all depends which way you're going or what you're trying to cancel out. Since I have moles up here, I have to choose this one because moles is on the bottom. Whatever's on top has to be down here at the bottom. Don't forget that, okay? So if moles is on top, moles will go on the bottom, and this is my conversion factor. This is the one I'm using, okay? So then what we do is we multiply the top by the top. So I take 2.12, I'm trying to find a pin here. So I take, these guys cancel out. I take 2.12, whoop, that's dried out, that's not good. Let me use dark blue. So 2.12 times 6.02 times 10 to the 23rd. Oh my goodness, we're back to that exponent again, aren't we? Ugh. So, and then we divide it by 1 to multiply the top by the top. Let me see if I can get my calculator to show up here for you guys. Let's see if this will help. I don't know if it will or not. Okay, there we go. So here's what I'm going to do. Watch what I'm doing. So, autofocus. Lock into place. There we go. So I take 2.12. Let me clear it all out. 2.12. And I'm going to multiply it by 6.02. What do I do? Second, comma, 23. Look what I have up there. This is what you need to have on your calculator. So you're multiplying 2.12 times 6.02 times 10 to the 23rd. This little e right here is your times 10. Do not put a times 10 in there. So then I hit equals, and my answer is a really long number. Oh, let's look at some sig figs here. Well, the thing is, sig fig or not, I want you to use 2 digits after the decimal, okay? It's going to work out that way anyway. But I've got 3 sig figs there, 3 sig figs there. So my answer is going to have 3 sig figs, which will give me 2 digits after the decimal. So my answer was 1.27624 times 10 to the 24th. Now do not forget this times 10 to the 24th right here. Okay, a lot of you guys do that. So 1 digit after the decimal, 2 digits after the decimal. Well, that's 6, in fact, that's 7. Yep, sure enough. So it'll be 1.28 times 10 to the 24th molecules is my answer. Okay, let's try another one. And give me a second. Let me pause this for 1 second. And I need to go get a water bottle. Am I recording? I don't know. Okay, I am recording. Good. So now I'm back to a clean slate again here. So let's say let's go back over the whole idea of these equivalent statements. Okay, just like I'd be saying 12 is the same as 1 dozen, right? And 1 dozen is the same as 12. Okay, so what if I said, I'm gonna make this A and this B, so you can choose. So what if I said you've got 492 donuts? How many dozen would that be? Okay, so let's look at it. Write down your given. Here's my given. 492 donuts. Line. I want to multiply it by something. Well, am I going to use A or B? If donuts is on top, and I'm sorry, let's make these donuts here. Donuts. So donuts is on top. What has to go on bottom on this side? Well, of course, the donut. Okay, so of course the donut's going to have to go on bottom. So am I going to use A or B to figure out how many dozen it'll be? Well, of course, I'm going to use B. So I'm going to say 12 donuts equals 1 dozen. Because see how we're looking for dozen? That should always be what's on top. Whatever you're looking for must be the last thing on top. That way this donut can cancel that donut out. And so I take 492 divided by 12, and I would have 41 dozen donuts. Yummy, yum, yum, yum. Okay? So that's basically what we're looking at. But instead of using something you're familiar with like donuts, we're using moles. And moles is just a count, just like a dozen donuts. Maybe not as delicious, but it is just a count. So when we're talking about particles, a particle, remember, particle can be an ion, it can be a molecule, it can be a formula unit, it can be an atom. So whenever you see any of those, you know you're working with particles and particles only. Okay? So let's say we have, so I'm going to write these two things down. So A, 6.02 times 10 to the 23rd particle, whatever it might be, over 1 mole, or B, 1 mole over 6.02 times 10 to the 23rd particle. Okay, abbreviated particle there. So let's say looking at, we've got 4.97 moles of copper. First, it's going to be an atom because it's an element. How many atoms of copper will that be? Okay, so we know this is going from moles to particles because we're going from a mole to an atom, and an atom is one of the particles. Okay, so the first thing you do, let's write down our given. What is our given here? Let me get this out of the way so I can scoot things to the back. So our given is right here, 4.97 moles of copper. I've got to multiply it by something to go from moles to atoms. Am I going to use A to do that or B? Which equivalent statement will I be using? If you happen to say A, you are correct because I have a mole on top. I need that mole on the bottom to cancel it out. So 1 mole over 6.02 times 10 to the 23rd atoms. That's my particle I'm looking for. Okay, so that mole cancels this mole out. And now we multiply these two together. So let's clear it out. Make sure 4.97. So I put 4.97 times 6.02 second double E 23rd. And I get 2.99. I'm not going to round it up because that 1 won't round that 9 up, times 10 to the 24th. So my answer is going to be 2.99 times 10 to the 24th. That's not that difficult now, is it? I mean, you know. Let's try another one. Let's just do a couple of these just to make sure we're all on the right track here. Let's see. Oh, I should have left those up there. So again, A 6.02 times 10 to the 23rd particles over 1 mole, or B 1 mole over 6.02 times 10 to the 23rd particles. Kind of messed that one up, didn't I? There we go. So let me move me down here then. Here we go. Okay, so let's say I have 7.96 times 10 to the 21st, I don't know, say 4 units. And I want to know how many moles that would be. So now we're going from 4 units to moles. So let's write down our given. Our given is any number that we've been given. So we write down 7.96 times 10 to the 21st. I'm going to write FU just because formula units is so hard to write. Not hard to write, just long. Now, in order to cancel out formula units and go to moles, am I going to use A, equivalent statement A, or equivalent statement B? You tell me, which one are we going to use? Well, if you said B, you are correct. So we're going to use this one right here. 1 mole, because that's what we're looking for. Whatever we're looking for goes on top. And 6.02 times 10 to the 23rd formula units at the bottom. You're like, well, Ms. Cottingham, you have particles over there. Remember, formula unit is a particle. So formula units cancel each other out. Let's put this in our calculator. So we have 7.96, second E, 21. This is 7.96 times 10 to the 21st. That's what that means. And now we're going to divide it. You multiply the top by the top, and then you divide it by the bottom. These guys are multiplied, and when they're on top of each other, they're divided, okay? So we're going to divide it by 6.02, second E23. Oh, look at that number. It's very, very small. So we have 2 digits at the decimal. 1 digit here, 1 digit there. 0 does not count. Please remember that. So your answer is going to be 0.013 because that 2 will not make that 3 round up. So it's 0.013 moles. Easy breezy, right? Okay, so I'm going to give you a minute. You're going to do a couple of these for me, and then we'll come back and we will continue on because we got a little bit more to go. Will that be exciting? Okay, so hopefully you got your practice of particle to mole and mole to particles all done and all good. So now we're going to move on to the next part of this thing. It's called a mole map is what we use. That's the map you saw on the very first slide. A mole map helps us go between different units in the mole, okay? So the next thing we need to talk about is something called atomic mass and molar mass. Now, we talked about atomic mass back in chapter, I guess it was 6, maybe we were talking about the periodic table. So atomic mass is the mass of a single atom. Now, typically it's measured in something called AMUs, atomic mass units. But we use grams because we really can't work with atomic mass units. So we use a larger amount of the substance and measure it in grams. So the atomic mass is found on your periodic tables. It's at the bottom of your little box, the number at the very bottom of your box. That's the atomic mass. Remember, the atomic mass is an average of all the different isotopes that we know of that element. It's a weighted average, but right now the atomic mass is just this number at the bottom of each box on the periodic table. So you will definitely need your periodic table out right now. Right there is a number. Now, if you look on your periodic table, so silver has an atomic mass of 100.7, carbon 12.01, and sulfur 32.07. These may be a little bit different than your periodic tables just because they're rounded a little bit differently. But that's where you find the atomic mass, is in the bottom of the box on your periodic table. Now, atomic mass factors, I don't know if I'd call it that, but basically it's just like what you did with the mole, the particles. So in order to look at the atomic mass, we know the atomic mass of one phosphorus atom is 30.97 AMUs, okay? So we're gonna be looking at them like this. And let me go back to the other one real quick, going back and forth here. So basically, we say this. Now, we'll say 1 mole of phosphorus is equivalent to, what is it, 30.97. 30.97 grams. We're not using AMUs, okay? So you look on your periodic table and you find phosphorus, and which is right here in 30.97. So 1 mole of phosphorus equals 30.97 grams. Or I could say there are 30.97 grams in 1 mole of phosphorus. It's an equivalent statement, just like before. Okay, so let's go back to the, okay, so these are conversion factors. Now there's something called molar mass. Molar mass is the atomic mass of 1 mole. I kind of got ahead of myself, okay? So a molar mass tells us 1 mole of something equals this amount. So 1 mole of mercury equals 200.59 grams. 1 mole of carbon equals 12.01 grams. 1 mole of iron, 55.85 grams. And 1 mole of sulfur, 32.06 grams. So 1 mole of anything equals its atomic mass, okay? And we call it molar mass because it's 1 mole of it. And that's how we deal with, molar mass. So molar mass is the total mass of 1 mole of atoms in a compound also. So not only does it go for single elements, it also has the same effect on compounds. So for example, if I have sulfur trioxide, means I have 1 sulfur atom and 3 oxygen atoms, right? So here's my 1 sulfur, here's my 3 oxygens. Well, what I would do is look up the mass of sulfur. The mass of sulfur is 32.06 grams. The mass of each oxygen atom is 16. So I have 32.01 or 0.1, rounded up, plus 16, plus 16, plus 16 gives me a molar mass for that compound of 80.1 grams. They keep saying AMUs, but we're using grams. Okay? So let's go back and let's try it over here. Let me stop sharing this. I know you're going to get like slingshot, woo, back and forth. So let's practice some of these. So I said 1 mole of phosphorus equals 30.97 grams, or 30.97 grams equals 1 mole. So look at your units. It's grams per mole or moles per gram. So that's how we look at the units for this. Now, what if I have water? 1 mole of water equals 18.00 grams, or 18.00 grams equals 1 mole of water. You're like, well, Sam, how'd you know that? Well, let me shed some light on that for you. Water is made up of 2 hydrogens, right? So 2 times its atomic mass, which is 1. So 1 equals 2.00. And oxygen, there's only 1 oxygen there, right? So it's 1 times 16, which equals 16. You add these two together. So it's 18.00 grams. That's how you do molar mass. Okay, so molar mass is actually really, really simple. Let's try a few molar masses just to get that under our belt first. Atoms is easy because you just look at the periodic table, but let's look at molar mass here. So let's say we have K2CO3. Well, how many potassiums do I have? I have 2. And I multiply it by potassium's atomic mass, which is 39.10. So 39.10. And then carbon, I have 1 carbon. I multiply it by 12.01. Look at your periodic table. Carbon's 12.01. And then oxygen, I have 3 oxygens. So 3 times oxygen 16, 16.00. So I have, so 39.10 times 2, 78.20, 12.01, and 48.00. So I multiplied these two and got that, multiplied these two and got that, multiplied these two and got that. Then I add these together. So 1, 2, 16, 17, 18, carry the 1, 7, 8, 9. So it's 138.21 grams per every, I can't do like that. Sorry, I told you not to do that. Grams for every 1 mole. So 1 mole of K2CO3 equals 138.21 grams. It's grams per mole. Let's try another one. It's fun. Okay, so, let's do a fun one now. Let's look at magnesium hydroxide. This is why formula writing is so important, okay? So, I have magnesium. How many magnesiums do I have? Only 1. So I have 1 times 24.31. I looked at my periodic table and got that mass. It's right there, okay? Okay, so it's 24.31. Then I take my oxygen. Now notice there's a 2 out here. There's 2 oxygens. 2 times 16.00 equals 32.00. And I've got 2 hydrogens. So 2 times 1.00 is 2.00. And together, 1, 3, 8, 58.31 grams for every 1 mole. Make sure that's right. 4, 8, yep, that's right. So equals 58.31 grams for every 1 mole. That's why if you write magnesium hydroxide like this, MgOH2, you're going to get the molar mass wrong because you only have 1 oxygen, not 2. So you need to make sure you know how to write your formulas. Okay? So I'm going to give you a few minutes and practice doing this before we move on to more conversions. So give you a minute here and let's pause the recording so you can do some work. Okay, let me make sure. Okay, good. So now that you know how to do molar mass and you know atomic mass, now we're going to convert from moles to mass. Fun, fun, fun. Now, instead of my trying to write it on the screen, I'm actually going to do it on the whiteboard. But anyway, I want to show it to you first. So you got to remember, 1 mole of any substance is equivalent to its molar mass. That's a little different than 1 mole of any particle is equal to 6.02 times 10 to the 23rd. These are 2 different things, okay? And we go from moles to mass, we'll be doing something different. So let me go to my whiteboard. Oh, no, don't want that. I want this. Okay, so now you had this before. So here's a mole. And first thing we did was we went from moles to particles, right? And going mole to particle, we did this. I'm going to use a different marker with a little finer point. So when we went from moles to particles, like this, when you go this direction, you have 6.02 times 10 to the 23rd over 1 mole, right? Now, if we go this direction, you're going to have 1 mole over 6.02 times 10 to the 23rd. That's what we just covered a few minutes ago. But now we're going to go from moles to mass. And that's grams, by the way. Whoop, let me write it down a little further. Mass over here. Okay, so now when you go between, let me find my other pen here. Alguro. Oh, here it is. When I go from moles to mass, like this. So I'm going from mass to mole. So whatever I'm going to goes on top. 1 mole over the molar mass of whatever I'm looking for. Okay? And if I'm going from mole down to mass, it's the molar mass over 1 mole. Okay? So here's what we're going to do. We're going to do a few of these. Now, we're not going to look at this part right now. This is just from what we did last time, okay? So we're going to focus on this part right here. So if I say you've got 4.67 moles of copper 2 oxide, I want to know how many grams will that be. So we are going from moles, because that's my given, 4.67 moles of copper 2 oxide, and we're going to mass. So I'm going from moles to mass. I'm going from here to here. So I'm going to follow this line right here. So which am I going to use? A or B? Well, I'm going to use B because if mole's on top over here, mole has to be on the bottom down here. And that says the mole's on the bottom. So I got to find the molar mass and put it over 1 mole. Well, the molar mass of what? Well, the molar mass of copper 1 oxide. Okay? So I have to get out my periodic table and look up the mass of copper, which is 63.54 grams. So I add 63.54 to oxygen, which is 16. And I get 4, 5, 9, 7. 79. I added these two together, 79.54 grams. So I put 79.54 grams for every 1 mole. Does that make sense? That way the mole on top cancels out that mole on the bottom, and we're left with grams. That's what I'm looking for. So I take my calculator, I multiply the top by the top. So I take 4.67, and I multiply it by 79.54, and I get this, 371.4518. 2 digits after the decimal, guys. 2 digits. So 4 and 5. Will that 8? Will that 1 affect that 5? No. So my answer is going to be 371.45 grams. That's how you do mass to mole and mole to mass. Let's do a few more. Okay, let's say I'm going to have, let's do 4.26 moles of NH4I. How about that? Okay, and I want to know how many grams that is. So again, I write down my given, 4.26 moles of ammonium iodide, NH4I. I got to multiply by something, okay? So give me 1 second. I got to get something off my screen. There. And so what do? I have to look up the molar mass because it's molar mass over 1 mole. The mole is going to go down here at the bottom because there's a mole up here at the top. I want these two to cancel out. And the top is molar mass. So I have to add all this up. So nitrogen is 14.01 grams. Hydrogen is going to be 4.00 grams because there's 4 of them. And iodine is a really big number, 126.90. So when I add all these together, I get a 1, a 9, I'm going to 10, 14. I got them outlined here. 14, 2, 3, 4, and 144.91. So 144.91 grams. 26.9. Check my math here. Plus 14.01. Yep, good job, Nick. Okay, so that mole cancels that mole out. I multiply the top by the top. So I take 144.91 and I multiply by 4.26. And I get 617.3166. My answer is going to be 617.32 grams because that 6 will round that 1 up. I'm going to try one more since I kind of did the exact same one as before. Let's flip it around a little bit. Okay, so what if you've got 319.21 grams of lead, and I want to know how many moles that would be. Okay, so I write down my given. My given is going to be this number here, 319.21 grams of lead. And I want to multiply it by something to get rid of grams and to get the moles. Am I going to use A or B? Well, I'm going to use A because mole is on top and that's where I want to go. So 1 mole is equivalent to the molar mass of lead. So I have to look lead up. I go over here, 207.20. So I write down 207.20 grams. I don't have to do anything else. It's a single element, so that's okay. My grams cancel out. And now I divide 319 by 207.20. So 319.21 divided by 207.20. And I get 1.54. So my answer is it's going to be 1.54 moles, which makes sense because if 1 mole is equal to 207, and I start off with 319, it's going to be just over a mole. So it's like saying I've got, 18 eggs. How many dozen will that be? Well, if a dozen equals 12 and I have 18, it's going to be more than a dozen. So make sure your answer makes sense, okay? Always make sure your answer makes sense. Hopefully this is a little understandable for you. Let me see, let me stop sharing here. Make sure I've got everything else done. Share screen, go back to basic. Sorry, I didn't mean to be telling you okay. Yep, then we're gonna practice mass to mole and mole to mass. And I think that's what we're gonna finish up with today. So finish this on Play Pause It. Make sure you turn all your work in, and then Mr. Reeve will put together a like a quiz for you. And if you have any questions, you know where I am. I will talk to you guys later. And let me stop sharing this and say goodbye properly. Bye. Let me know if you need help.